Thank you. So this is joint work with Malte Helmert, sitting over there. And I want to start with a short quiz. I hope you're all prepared. You know, this is going into your final mark for ICAPS. So the first question is, assume you have an operator that unconditionally sets variable a to the value 1. What transition does this operator induce in the domain transition graph for A? And does O actually produce the fact A maps to 1? And the second question is, if your only goal is to set A to 1, what is the goal value of B? And what is the regression of this goal with the operator O from question 1? So you might have figured it out already. In the first part, I'm just showing you the answers so you don't think about the questions during the whole talk. The first question is actually a bit of a trick question because I asked for the transition, and it's actually multiple transitions that are induced. There's one transition for each value of A. For the question B, the problem is that the operator can produce this value, but it doesn't have to, because the value can be true before you apply the operator, and then you wouldn't say the operator produces the value. For the second question, the goal value of B is actually not important, so any value of B would be fine. And for the last question, if you regress the goal over this operator, any state would be possible as a previous state. So these questions are not impossible to answer, but my point here is that they would be easier to answer if the operator actually had a precondition on A, and if the goal actually had a value for B. Then those questions would be easier to answer. So this is what we are doing here in the short paper. We want to restrict the attention to tasks of a simpler type, of a simpler form. And of course, we don't just want to say that we are only considering the simpler task. We also want to show that general tasks can be transformed into this simpler form. And we want to transform them into an equivalent simple task. And equivalent, of course, depends on what you're trying to do. If you're working with landmarks, equivalent means that all of the landmarks still are landmarks in the transform task. If you're just interested in shortest paths, equivalent means that shortest paths are still shortest path in the transform task. So I first want to introduce the type of task we're trying to consider here without mentioning the transformation yet. So just what we would like the task to look like. So we say a task is in transition normal form if all operators mention the same variables in the precondition and in the effects. So that would exclude the example from the quiz. And we also want that every variable has a goal value. Okay. So there is one transformation into those tasks, into tasks of those kinds that's been around, and that's one of those things that pop up here and there, but we couldn't really find a definitive source for that. So if you have an operator like this that has no preconditions and two effects on A and B, you would multiply out this effect. So you would have every possible value for A combined with every possible value for B, and for each of this combination, you introduce a new operator. So in this case, it's just 4 operators, but I think it's easy to see that this is an exponential increase. So you could theoretically get an exponential number of new operators. So what we are trying to do is to give an alternative transformation which only increases the task size by a linear amount. And the main idea of this transformation, which we call the transition normalization of a task, is that we allow to forget the value of any variable at any time free of cost. So we do this by adding a new value, which we call u, that represents that we forgot about the value of this variable. And then we add operators that allow to forget the values, And whenever we want to have a precondition, for example, in an operator or in the goal, we just add the value u instead. So a bit more technical. Like I said, we add one new value to the domain of each variable. And for each fact of the problem, we add one operator that has this fact as the precondition and sets the variable to u. So this is effectively forgetting the value of the operator, the value of the variable. And of course, this is free of cost, because we want to be able to do this all the time. Whenever we have a precondition without an effect, this is actually the easy case, which is also done in the other transformation, but I skipped over this. Whenever we have a precondition without an effect, we just add the same fact as an effect, because the operator doesn't change it, so we just leave it as it is. The other direction is the more complicated one. If we have an effect without a precondition, then we add this artificial precondition for the variable. We want that the variable has no specific value, that we forgot about the value of this variable. And the same thing we do for goals. Whenever we have a variable that does not occur in the goal, we explicitly add the goal fact that this variable should have the value u. So here's a short example. Assume we have an operator that has b maps to 0 in its precondition and a maps to 1 in its effect, and a goal that only has a maps to 1. So we get 4 forgetting operators for each possible fact of a. Here I'm assuming binary variables just because just to keep the example small. But of course, if there were more values, we would just get more forgetting operators. And it should be easy to see that we get a linear number of operators, not an exponential number of operators here. So yeah, for each fact, we have one forgetting operator that allows us to forget the value of this variable. We also have to modify operator O because it has some variables that only occur in the effect and some variables that only occur in the precondition. So B only occurs in the precondition. So we add the effect B equals 0. So that basically changes nothing because if we add B equals 0 and it was true before, then it doesn't affect anything. But the operator also has an effect on A, but no precondition on A. So we explicitly add the fact that A maps to U. And we can always achieve this fact by just applying the forgetting operator that we need. Just as we modified the precondition here, we also have to modify the goal. The goal doesn't mention B, so we add B maps to U in the goal. So the first interesting property is that we can transform tasks from a task to its transition normalization, which I write here as T and F of pi, by just inserting forgetting operators whenever we need the value of a variable to be U. We can just add these operators, and they won't increase the planned cost. We can also transform tasks of the transition normalization back to plans for the original task by just dropping all forgetting operators, and this will also have the same cost. So for the rest of this talk, I will talk about which properties are maintained by this transformation and which are changed, and finally when and when not to use this transformation, because you might think, if you think about regression, maybe I had a discussion with Alvaro and Christian before that this might make not sense in regression. Wait till the end, I'm going to talk about this. But first I'm going to talk about heuristics. So for delete relaxations, you might know this, but the delete relaxation just ignores the delete effects of an operator. And there we have the nice example that a task and its transition normalization have the same delete relaxation heuristic. So it's the same for all states from the original tasks. Of course, we can say things about states that contain these new facts. The next class of heuristics is critical path heuristics, which is the class HM that consider fact sets up to size m. Excuse me. So for each set of facts, HM assigns a value to this fact set that corresponds to the cost of reaching this fact set while only considering fact sets of up to size m. And this class of heuristic is particularly important because the special case of m equals 1, h1, is the hmax heuristic. And we have the result here that the hm values for fact sets actually match in the task and its transition normalization. And that, of course, directly implies that also the heuristic value for hm is the same for all states from pi. Okay. For landmarks, we get a similar result that landmarks that don't contain forgetting operators are the same in both the task and its transition normalization. And with the help of the result about hmax, we can also say that the LM-cut heuristic will discover the same landmarks in both cases if you break ties in the same way. So the last class of heuristics is abstractions. And abstractions actually do change. So it's not the case that just everything stays the same. We introduce new operators and those change transitions. So abstractions may change. But we have a very nice result about domain transition graphs. Domain transition graphs are widely used in heuristic search. They model the effects of an operator on a single variable. And while they are not the same, they actually behave nicer in the transition normalization because every operator defines a clear value transition in the DTG for each variable. It's either is a self loop or it is a clear transition from one value to another. Which also means that the number of transitions we can have in a DTG is linear in the number of operators and no longer quadratic as it was before in the original task. A final heuristic I want to talk about are potential heuristics. They are also in the class of abstraction heuristic. If you want to know why, you should go to Jendrik's talk in the joint SOX and ICAPS session. They are a recently introduced class of heuristics that express the heuristic value as a weighted sum over the facts in the state. And the weights of this weighted sum are constrained in a way so that the resulting heuristic is admissible and consistent. And because they are constrained, because they classify admissible and consistent heuristic, we can actually generate the best potential heuristic this way. Best according to any criteria. And here are the constraints for a task in transition normal form. And they're actually very clear and make it clear what's going on. So, for example, we want the goal state to have a heuristic value of 0, which we can just say that the sum of all goal facts is 0. And for all operators, we also want that the change the operator has in the heuristic function is at most the cost. So this is the consistency condition. So these constraints are very clear. If we would consider general tasks, these constraints would be much more complicated. We would need additional variables. We would need a function that handles the cases where we don't have preconditions. Here, transition normalization helps to make it clear what's actually going on. So I finally want to mention two more techniques, just very briefly. The first one is Zobrist hashing. You might know this from games like chess. The idea here is that we associate a random bit string with each fact, and then hash a state by XORing all of these bit strings together. since we, when we apply an operator, we can XOR all the bit strings for all deleted facts and for all added facts, and we will get the hash value for the new state. But in the transition normalization, we actually know in advance what the deleted and added facts are. So we can pre-compute the change an operator has in the hash value and only need one XOR operation to generate the new hash value. And a very similar application of this is perfect hash functions that is actually used in the implementation of PDB heuristics. Okay. I'm almost out of time, but I briefly want to mention regression. The nice thing about regression with transition normal form is that you always work on full states, and you can just switch precondition and effect and initial state and goal state, and then have a search that works just as progression, and you always work on full states. So the question is, should I actually use this in practice? And the answer is no, not for regression. Definitely not for regression, and also not for forward search, probably. The size of the reachable state space can increase exponentially, so you shouldn't use it in cases that depend on the size of the state space. Instead, you should use it as a theoretical tool to design and analyze heuristics and prove properties of your heuristics. You can use it in practice, but only on things that are polynomial in the description size of the task, not in the size of the state space. So in conclusion, transition normalization gives you a linear increase in task size while transforming tasks into this normal form. It can make it easier to to define concepts and thus help you design and analyze heuristics and see what's actually going on. Thank you.